Woo. Good day, everybody. Yes, my name is Fabio, and as it is trendy to say today, of course, I am an engineer. That was meant to be my ice-breaking sentence, sorry. Yes, actually, you may be wondering why these two pieces of equipment, and I'm going to explain it to you in a while, but first of all, I would really like to start from a quote by one of the 5 good emperor, Marcus Aurelius Antoninus. Marcus Aurelius Antoninus had empowered the power of observations, individual observation. Practically, he asserted that nothing is such powerful than having a systematic way of investigating and also observing things individually in truth. This was a very big sentence, strong sentence, and the reason why I've been choosing that is because of a good connection between what I'm going to explain in a while, and it will hopefully makes clear the connection between these two equipment. Systematic observations and observation of real-life cases. So, to give you a bit of more understanding about these two pieces of equipment, here we have a stereoscope. It's a piece of antique stereoscope. It's been for ages with me, and finally I found a function for it. And it has been developing in many forms, and behind me you have a nice piece of tabletop French Victorian stereoscope, Stereoscopy. Stereoscopy was pioneered by the British scientist, physicist, Sir Charles Wheatstone, and actually it was a breakthrough advancement in optical science. And equally, the other piece of equipment, this box in here, is called ground-penetrating radar. Actually, it's got many names as per the applications that it's being used for. But the most conventional one is ground-penetrating radar, also known with the acronym of GPR. For ground-penetrating radar, I've chosen a date which is universally recognized as the date of the first ever published record in GPR science by the Egyptian researcher El Said, 1956, who managed to image the water table depth surface in a desertic area. Actually, I'm trying to make a point, but I can see still the connections between these two is not clear. So why I've been choosing these two pieces of equipment for a talk which is engineering focused and also is looking at the concept of observations. So actually, why observations? Why these two pieces of equipment for observation? I think it is fair on me to give a bit of background information about what is the historical impact that these two pieces of equipment had, and also how can be the implications of these two equipment into future advancement, and how this can push the boundaries of engineering science towards a new concept of observation. Well, starting from the GPR, so this nice white box in here, well, it is very much well known for its main peculiarity. The main peculiarity of ground-penetrating radar is to have a penetration of the subsurface using electromagnetic waves, and with the capabilities of image the subsurface without altering it. Actually, if I would like to be a bit catchy in my expression, obviously, accounting for all the boundaries dictated by science, I would say that this piece of equipment is capable to see the unseen. As well as this dimension, GPR is very much popular for being relatively fast and also for being pretty much versatile in terms of the applications area. And I can literally name dozens of areas that GPR is been applying on. Archaeology, to reconnect with the original sentence that I started the talk with, Mining, actually the military industry was the original industry where GPR has got its first development. Civil engineering, infrastructure monitoring, bridges, tunnels, also geological application. You may have heard of using GPR in planetary explorations, lunar exploration, more recently Mars explorations. And I've picked one that in my view is one of the most fascinating, is the applications of GPR in glaciers actually, for ice as no thickness assessment. That is the case of having this piece of equipment with an odometer, so an encoding wheel that record the signal whilst it is dragged, and it can be dragged at walking speed, it can be attached to inspection vehicle, or more recently, drones are being used to reach very remote areas. So whilst the signal is encoded, then the information is collected in many forms. This is another peculiarity of GPR. One of the most popular is the one that you see at my back, and it's called radargram. Of course, what you can see there, it's at the back of a processing, and processing, it requires expertise. Not always, because of physical constraint, we are capable to pick up features that we are looking for. However, that is a good example of an application of GPR in an ice lake in Canada, that, as you can see, it has depicted quite nicely the horizontality of the layer of the geology behind the lake. So that's the power of GPR. So I would say this technology, again, reconnecting to the original title of the talk, it can actually enhance our level of understanding. It can add a dimension to our level of understanding. That's the main peculiarity. So, what about the next one? Well, stereoscopy, as I said, was invented in the first half of the 19th century. And actually, the concept is that the mind combines two-dimensional images to create the perception of depth. This concept was back to thousands of years earlier by the Greek mathematician Euclid, who said first that the combination of views from right and left eye and the processing that is done by the brain, it creates the sense of depth. Obviously, technology has advanced, and using the capability of optics, that has become this piece of equipment. And using 2D images like the one on the slide, Coliseum, or the one that I have with me, again, it came out for ages, and it's a stereoscopy image of the Vatican museums, very nice. It created the sense of depth that you can see reproduced in the stereoscopy image that gives the perception of depth, and that is coming from the British Museum, from the photographer Fenton. So I said, what's next? Because actually, the area of computer has triggered another dimension to the concept of stereoscopy. It allowed us literally to produce very sophisticated three-dimensional generated model, and nowadays that comes up to immersive technology. So we can say that stereoscope was the first of its kind in immersive technology. I'm sure everybody of us had experience, even sometimes we are not aware of it, of using immersive technology. It could be virtual reality, so when the digital world takes over and the real world is shut out. It could be augmented reality, when there is the digital world on top of the real world, or it could be mixed reality, when there is an interaction between the digital and the real world. So this industry, it has been said before, it has got a big market, and it's with us every day. We are talking about something that can produce global revenues back to 2023 of nearly 26 billion pounds, with the forecast in terms of growth rate, percentage growth rate, of 25% estimated in 2030. So an industry which is with us, and it's making available technology every day. So again, to go back to the concept of observation, this type of technology can definitely help ourselves to enhance our sense of understanding. So then we have one technology on one hand that enhances the level of understanding, and the other technology enhances the sense of understanding. So I hope I'm trying to make my point. Is this really a new era that we can say that observations are undertaking a paradigm shift towards an observation 4.0 era? Now, this is to be proven, and I'm trying to give you an account of a few case studies that cover different areas of engineering and beyond. I will start with what, in my view, is a standard conventional engineering process, where you study a problem, so you start from site investigation, and then site investigation with validations that are required in engineering problems, and the light processing steps where the target is started to be identified. You remember, I recalled it earlier, radargrams. Now you can see the sequence of processed radargrams where eventually, in this case, we were looking for 3 routes. The targets were identified. However, this is an image of something that has been identified in a 2-dimensional domain. Is it something that is still undergoing the engineering process? And that is what is the next step. The next step in an engineering process is towards the creation of algorithm. So it's the design of algorithm. Again, in this case, the aim was to put the information that we got from the radar into a 3-dimensional view, or looking for physical parameters like the shallow and the depth and the deep roots, or the mass density of roots. Mass density in identifying roots is a very important problem because it can tell you a lot about the health of trees. The next step is the 3D computer-generated model. So providing an enhanced understanding of what is the engineering problem under investigation, 3 routes. And then you can see better, for example, interactions. You can see areas of overlapping, et cetera, et cetera. I put a raising flag there because the concept is this. Is this really the boundary? Can we push the boundary towards the next level of information? Well, referring to that case, again, 3 routes, and using the potential of immersive text, in this case, virtual reality, we have imagined that, and then proven, we have imagined that it was possible to overlay informations that come from the unseen, GPR, with informations that are available and scanned for the environment. And those informations combined together into a virtual environment can allow next steps, next process. Now, I'm going to show you a video in a while, and I would like to use your imagination. Unfortunately, there is no way for me to provide you with an immersive big machines that allows you to experience, but probably you have seen the movie Ready Player One, no? Where there is an immersive reality and then interactions with the reality. So imagine yourself to be totally immersed in this environment, and with remote control, going there and looking at areas that you have investigated. This is the case of 3 routes inspections, where information from the underneath that you can see from that blue pieces of radargrams are overlaid with the terrain. And at some point, there is a route that we have excavated for validation purposes, engineering process, that matches the reflections. Can you see the power of this? Can you see the power of studying this problem in an immersive environment with stakeholders, asset owners, managers that they need to take decisions? Industry-related concepts, and education. So there's lots of fallouts. There's lots of implications that comes after this type of approach. Of course, this is just one example, but I can make others in the same field, environment. This is the case of a similar concept applied to tree trunks investigation. In here, in a similar manner, radar information have been overlaid with a digital model in 1-to-1 scale of a tree trunks. And you can see that there is a good matching between the holes in the tree trunks and also areas of porosity. Now imagine yourself analyzing a living tree and looking at this in an immersive environment and looking at the data that they deploy across time. You can see the evolution of the damage, another very powerful concept. Now, we touch-based virtual reality. Now, we say that immersive is made by many other technology, and I would like to showcase another case study that is significant to showcase the power of immersive, augmented reality. Here is the case of a different type of radar system. We are here referring to an interferometric radar. These systems are remote sensing systems, so they work at very large distances, and they are very proficient. However, they need referencing. So they need a reference target to be monitored, and then the response is associated to that. So what's the point of this? It means that we need to know the context information. And that is where augmented reality can help us. What I'm referring to is that this type of radar, as any radar, they've got a beam of radiation. And the beam of radiation is something that we know it's there, but cannot be visualized. Now, the question is, can we provide any information that can help us to understanding where the radar is actually hitting? This is what we've tried to do, empowering augmented reality and remote sensing terrestrial radar. Again, what you can see in here is reality, actually. So it's a recording of augmented reality tool developed to image the beam of radiation of a radar pointing towards a masonry wall. And you can see a cross-section that is formed. That means that we have now coordinates of where this beam of radiation is hitting the wall. It means enhancing the level of information again, which was not possible so far. Last but not least, reconnecting to my initial quote from Marcus Aurelius, archaeology. I would say archaeoengineering, because here the problem was really an engineering problem. The place is the Circus of Maxentius in Rome, which is the second circus for importance in Rome. Here we had the task of investigating the external world of the circus, specifically pointing at the location of terracotta pots. You say, why terracotta pots? Well, Romans, they used to utilize terracotta pots at the arcs, actually, of their structure in order to enlighten the power, the weight of the concrete wall. Well, this is one of the theories. Then, of course, there is lots ongoing with archaeologists and structurals, actually. However, our task was, is it possible to see these terracotta pots with our radar? Actually, the terracotta pots is the one that you can see at the top left. Don't look at my head in the picture. It's the other one. And there's got a dimension of 50 centimeters. And this is the result. Again, please use your imaginations to be immersed in an immersive environment in virtual reality. Actually, this is what has happened. The radar was literally passed in a very complex wall, and what you can see at the back of it is the reproduction of the radar response. Can you see how much this can be useful also in an immersive environment to understand the position of the targets, in this case, terracotta pots? And indeed, the dots that you see are where we have located the pots in order to have that answer to the big original question. It's a big potential that can solve very complex engineering problems in a very fascinating domain, such as that of the archaeology. Actually, to end off, I hope have provided a good overview of what's coming on next for non-destructive testing, specifically ground-penetrating radar and immersive engineering. I believe there is a big value into that, and I believe we are just at the beginning of this revolution. Thank you very much.